The big rocket moved. Then it stopped. That single, impossible fact hung in the air of the control room, heavier than any silence. Outside, the sky was still vibrating from the force of the launch, the air still tasting of burnt fuel and immense power. But on the screens, the data told a different story. The upward climb, so steady and powerful just moments before, had faltered. The line on the graph that showed velocity had suddenly plateaued and then dipped. This is the story of Atlas, a heavy-lift rocket engineered for precision. A titan designed to push enormous payloads into the unforgiving vacuum of space. It is built to never stop. But on October 21st, 2025, it did. The launch had been flawless. A pillar of fire. A pillar of smoke. Then, the telemetry line went flat. The rocket had slowed. In mission control, the shock was a physical thing. The plan, rehearsed 1,000 times, had just been thrown out. The calm female voice of the flight dynamics officer cut through the tension.
Stage 1 has lost significant thrust. Stage separation has not occurred.
Downrange cameras showed the rocket, a monument to catastrophic failure. On the massive screen at the front of the room, the orbital map lit up. A piece of the failing rocket was on a path alarmingly close to the International Space Station. The mood in mission control shifted from diagnostic to protective. The crew was alerted, moving to shielded parts of the station as every calculation aimed to keep their fragile outpost safe. Inside the International Space Station, the emergency alarm was a sound no astronaut ever wants to hear for real. It was a piercing, urgent tone that cut through the routine hum of life support systems. The crew moved with a practiced efficiency that bordered on instinct. They didn't run. They floated, pushing off walls and handrails to propel themselves toward the designated safe havens within the station's modules. Through the station's famous cupola window, external cameras sent a new set of chilling images back to Earth. The video feed showed a long, dark shadow moving with a slow, deliberate grace against the curve of the planet below. Then, the object that cast the shadow came into view. A jagged piece of metal, tumbling end over end. Then something hit the side of the station. It wasn't an explosion. It was a dull, solid thud, a sound that traveled through the structure of the station like a shockwave. The impact was followed by a small, jarring bump that shook the Destiny Laboratory module. A science rack filled with delicate experiments slid a few inches along its track before stopping with a clatter. For a heart-stopping moment, there was silence on the communication link. No one was hurt. The crew, now secured in the Soyuz capsules docked to the station, began their damage assessment procedures immediately. They spoke in calm, measured words to the team on Earth, their professionalism a bulwark against fear. For a single, terrifying beat, the only sound from orbit was the faint, amplified sound of the crew's breathing. Then the link was strong and clear again. Back on Earth, the teams at NASA ran their own checks with a frantic, focused energy. They were now dealing with two crises: a failed rocket, a damaged space station. They pulled up decades of past data from similar rocket families. They scrutinized every detail of the Atlas V's design, fuel flow schematics, and command logs. Every system had to be interrogated. Every electronic signature had to be made clear. The world was watching, waiting to know what had made the mighty Atlas stop in its tracks. Slowly, as data from recovered debris and telemetry logs were painstakingly pieced together, a clearer picture of the failure began to emerge. The culprit was not a dramatic explosion or a complex software bug. It was small, mundane, tragically overlooked. Investigators zeroed in on a single tiny seal in a high-pressure liquid oxygen line. The seal, a simple polymer ring, had one job: keep super-chilled, volatile fuel from leaking. It was an older component, manufactured years earlier, stored in inventory as part of a sub-assembly. It had been tested long ago and passed those tests. But under immense stress and cryogenic launch temperatures, the material became brittle. It cracked, a minuscule fissure. That tiny crack was enough. A high-pressure spray of liquid oxygen escaped. The cryogenic spray struck a nearby metal bracket not built for such cold. The metal contracted and warped, bending just enough to interfere with an adjacent sensor conduit. The engine didn't stop suddenly. Its performance degraded in strange, unpredictable ways. The flight computer read confusing sensor data and flagged erratic engine behavior. It interpreted the readings as a turbopump imbalance. The control software did what it was designed to do. It fired the small attitude control jets, the tiny thrusters used for steering. The intended fix was to correct the perceived wobble. But with flawed sensor data, the correction was wrong. A fraction of a second erroneous push changed the rocket's trajectory, sending it into a slight but unrecoverable tumble. Aerodynamic forces tore the vehicle apart. Pieces separated. Small bits of insulation, brackets, and fairing panels peeled away. Debris scattered like shrapnel. A fragment from the Atlas explosion reached low orbit, striking the International Space Station. The impact was a solid, resonant jolt. The crew's training took over. They moved to seal compartments, their voices a study in composure.
Houston, this is Station, the commander reported. We can confirm a minor impact event. We are proceeding with the depressurization check procedure.
ISS reports minor structural contact. The crew is safe.
The calm, methodical response became a testament to human resilience and the trust between crew and ground. This story began with the silence of a failed engine, ends with a quiet reveal and a small, hopeful lift. The ultimate cause was a simple polymer ring, a component so small it could fit in your palm. Its failure set off a chain reaction. 9 tense minutes, a shower of high-speed debris. A jolt felt hundreds of miles up in orbit. That small, brittle ring will be changed. New procedures will be written. All similar seals will be retested under more stringent, launch-like conditions. New inspection protocols will be added to the pre-flight checklist. This memory will be embedded in NASA's institutional knowledge. Teams on the ground worked through shock and confusion. They demonstrated the quiet professionalism that defines space exploration. They studied parts recovered from the ocean floor. They ran countless simulations on the flight software. They changed procedures for handling older inventoried parts. Those parts will now undergo recertification before flight integration. They added new sensors to the engine assembly, tiny electronic ears to listen for the frequency of a high-pressure gas leak, so such a problem can be detected much sooner. The work was tedious, exacting, and essential. The scene from the station, a dark shard tumbling over Earth, will remain. It felt like a horror movie intrusion into a serene environment. But the enduring image is not fear. The crew's calm faces on the monitor, their quick, efficient work to secure their home. Teams on Earth, leaning into consoles, working with diligence and care. They didn't just fix hardware. They reinforced systems of trust. They reinforced communication. They reinforced collaboration. Those 7 minutes of shock forced important work. The event tested emergency response and revealed strengths and weaknesses. Many hands in orbit and on the ground must move in perfect concert. The smallest, insignificant-seeming things can matter the most. It reminded every engineer. It reminded every technician. It reminded every manager to look again, to double-check, to never take anything for granted.